Hello, my name is Apsara Fight, course Math 24, Linear Algebra and Differential Equations, Section 3D, in fall 2020. The project I am presenting on is the Verhulst Model. So a man by the name of Thomas Malthus theorized that populations do not actually grow indefinitely, but they are limited by the resources in their environment. So things like food, water, land, etc. So at first, the population would grow exponentially, but as they approach their carrying capacity, or what their environment will allow the population to grow to, it would slow down. Later, a man named Pierre Verhulst developed a model based on this work. So to derive and understand the Verhulst model, otherwise known as the logistic growth model, first we need to understand exponential growth. So let's have P stand for the size of the population and T stand for time. In exponential growth, we know that the larger the value, the faster the value is growing. So let's have the change in population, dp dt, be directly proportional to the size of the population multiplied by some constant k. Taking the antiderivative of that, you can see that we do in fact end up with the exponential growth model. Now, for logistic growth, we want the function to initially grow exponentially, which is why the exponential growth model is here on the left term of the logistic growth model, Kp. However, as the population approaches the carrying capacity, we want to slow it down, hence the right term of the function, 1 minus p over k. This function works because as when p is low, let's take 0 for example, 1 minus 0, that's just 1, and we're left with kp, which is the exponential growth function. So when p is very low, it's just growing exponentially. When p is nearly at the carrying capacity, nearly at big K, we're left with 1 minus 1, and which is just 0, and so the change in population size is 0. So let's look at a quick example involving a seal population. Oops, my face is covering it. Where it's modeled by dp dt is equal to 8p 4 minus p over 1,000. So what is the carrying capacity of the seal population? Well, we know that when a population is at carrying capacity, it's not growing in a logistic model. So we're going to set dp dt to 0, and we're left with 8p 4 minus p over 1,000 is equal to 0. And then we can divide by 8p because we assume that the population is not at 0. And then we can add p over 1,000 each side and multiply by 1,000 to get a carrying capacity of 4,000 seals. These are the references I used, and I hope I explained myself clearly enough. Thank you for your time. Bye-bye.